Okay. So what I'd like to provide you in this lecture is a full description of the process we undergo to connect the macroscopic behavior of materials that are being stretched to the microscopic behavior of the interatomic bond stretching. And so what I'd like to do is just recap this notion of a cross-sectional area. If I take an object that has a shape, no matter what the shape I draw, that object will have a cross-section, which means if I slice it at any point, it will have an area that represents the shape of the object. And so this has an area of the circle, it's the area of the triangle. We could do a square, of course, but I think the picture is hopefully clear that cross-section is just defined as the area of the square, as the shape of the cut that I would make. Okay. So, that's cross-section. So each 2D slice has a shape. Now, if I take a solid wire, much like we did in the class, and I give it hang it from a ceiling and apply a mass to it, it's going to sit in equilibrium. So here's my mass. And if I zoom in on my wire, what I find, if I zoom in really closely with a big microscope, what I'm going to find are atoms, chains of atoms, and those chains of atoms are going to be connected by springs. Each connection between the atoms are little tiny springs that connect everybody together in my solid. And so our goal is to find the stiffness of this bond. In terms of the stiffness of my macroscopic wire. Okay. So what we start with always is the momentum principle. We know that delta P is equal to F net delta T. And from that we can derive everything. We can go, and so what I'm going to do is define some things. I'm going to say that delta P, well, it's going to be the net force, which is going to be, and I'm going to just call this K sub S of the wire times the stretch of the wire, minus mg times delta T. Okay, so there's the momentum principle. And of course these are vector quantities, but we know that it's a one-dimensional system. We're only working in the y direction. And so as a consequence, I'm going to switch very quickly to just be a 1D problem. Okay, so now we know that because this is 0, I can set Ks of the wire equal to mg. And so the Ks of the wire is equal to, that's got an S, I'm sorry, mg divided by S. Okay, now, my wire, I'm going to say, has a cross-sectional area. I should get this in the right color. So my cross-sectional area of my wire, of course, is going to be whatever I deem it to be. I'm going to zoom in a little bit on my wire. Not as much as I did before, but here's a cut through my wire. And this is my cross-sectional area, A of the wire. And each atom, if I zoom in even more, each atom itself will have a cross-sectional area, in this case, a very small little box that will contain one atom. And so it's going to have the cross-sectional area given by A atom. So I have two cross-sectional areas. And so I'm going to call this D of the wire, this dimension. It's a square wire, D sub W. And A sub W is equal to D sub W squared. It's an approximation. I don't need to, it's not even an approximation. This is a square, so it's DW squared. But for the atom, I am going to make a slight approximation, and then I'm going to say that this little box has dimensions D atom, and so that's going to be D sub atom squared. Now, if I think about the number of chains that are in this wire, that make up the wire, well, that's the ratio of the areas. If I were to grid this into a grid of the number of wire chains this way, the number of wire chains this way, the ratio of these two areas will give me the number of chains. So N chains in the wire is the ratio of the atoms, the number of the area of the wire divided by the area of the atoms. Okay, so that's one thing to keep track of. That's the number of chains in my wire, the length of my wire. Then I can grid that. Now what I really want to know, the other thing, is the number of bonds in a chain. How many bonds are there to go from the top of my wire to the bottom of my wire? How many bonds are there? I just need to count them. The way I would count them is I would take the length of my wire and I would divide that by the diameter of an atom. L divided by D atom. That gives me a number. I've removed the units, right? This is a length, this is a length, this is a number, this is a number. I divide them, I get a number. Okay. The number of bonds from end to end. That's this. Okay, so those are two things to keep track of. So, what if I want to know, for example, what if I want to know, if I have a group of springs, now I'm just going to take my springs between my atoms. I'm going to zoom in a little bit more here. And of course I have one species of atom, so I only have to worry about one style of bond. So here are my bonds. And each bond has a stiffness. And so I have here 1, 2, 3, 4, 5, 6, 7, 8, 9 bonds in series. And so what we know, if we have springs in series, that 1 over K effective is equal to the sum of all of my k's. K1 plus K2 plus K3, 1 over K3 plus dot, 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 forever. But I know exactly how many bonds I have. And remember, if K1 is equal to K2, is equal to K3, is equal to K4, is equal to Kn, then 1 over K effective for n bonds, n springs in this case. Bond is a spring, so I could say n bonds here, is the number of springs or bonds divided by K for each bond. Okay. So now I can just say that each one of these is K. And write on here that the value is K. This becomes the number of bonds. If I want to know the number of bonds, just write it like this. So the effective spring constant of a single chain looks like this. It's 1 over the effective is equal to the number of bonds over K. Okay. So I'll just rewrite it. K of a chain of atoms is equal to the K of a bond divided by the number of bonds per chain. That's pretty straightforward. I can get you the K, the effective spring constant of a chain of molecules, atoms. Okay. Now, if I want to know the K of the wire, well, all I have to do is figure out how many chains I have in my wire. So if I know the K of a chain, now all I have to do is multiply that by the number of chains. Because these would be in parallel. This one is in parallel with this one, is in parallel with this one. I can ignore the bonds between them for now. I don't have to think about that. All I have to think about is now I have all of these chains in parallel, and that's just the sum of all of my bonds, or all of my chains together. So if I want to know the wire, I have to know the K of a chain, which I have here, and the number of chains that I have in total. Okay, so K wire, K of the wire, that's this entire thing, has to be, well, the K of atom, and I'll call that bond, like I did up here. K of a bond, divided by the number of bonds per chain times the number of chains. Okay. Now, that's kind of nice. So now what I can do is I can manipulate things in terms of the things I already know. So if I know the stiffness of the wire, which I can do from a macroscopic measurement, we've already done that. We know what K wire is. K wire, well, that was just mg divided by s, the stretch of the wire. That's a known quantity. K of a bond, maybe I don't know that. Maybe I want to figure out how stiff a bond is. I just have to multiply by this ratio, 1 over that ratio, and now I can do it. So let's do it. So K of a bond is equal to K of the wire times, well, this goes on the bottom, this goes on the top, number of bonds per chain divided by the number of chains. So 2 numbers. Okay. So if we want to know how stiff that one spring is, now what I can do is rewrite this. K bond, K of a bond between atoms is equal to the K of the wire, a macroscopic experimentally determined quantity, times a geometric quantity, number of bonds per chain, divided by the number of chains. Chains of atoms. How many of these exist? Well, if we fill all that in, K of a bond is going to be equal to, well, mg divided by the stretch of the wire times, okay, number of bonds per chain, we wrote that down before. That's going to be d squared over, d of an atom divided by d squared of the wire. Remember, just geometry, times the length of the wire divided by d of an atom. So that's the number of bonds per chain. That's this quantity. And this is 1 over this quantity. So what I can do is I can cross out this. So K of a bond is equal to mg divided by s times the L of the wire times the size of an atom divided by the area of an atom. That's it. That is the answer. So, let's write that one more way, and then we can put a box around it. So I'm going to put things here in terms of a couple interesting quantities that go together in my mind. K of a bond, of a single atom. So this is an atomic bond. The strength of an atomic bond is equal to, well, mg, acting on a mass that's hanging from my macroscopic object, times, well, here's the L of the wire. That's L naught. L naught over S. I'll bring my S and my L naught together. They go together because they're macroscopic quantities. The stretch of the wire and the length of the wire. That looks remarkably like something I would put into an equation about a spring. So L naught over S. That's macroscopic. Macro tells me something about the wire. Then I multiply that by a microscopic ratio of things. The size of an atom divided by the area of an atom. Oh, I'm sorry. Oh, I'm sorry, not of an atom, of a wire. Of the wire. D squared wire. I apologize. Wire, not atom. D squared wire. I apologize. This is not, this is brought down from here. I put atom here. It's the area, cross-sectional area of the wire. So now I have a macroscopic thing, purely macroscopic, and now I have the ratio of the size of an atom to the area of the wire. That's interesting. Okay. That is our answer. The stiffness of a bond depends both on microscopic things and on macroscopic things, mixed together in this interesting way.